Okay, and let's continue with looking at phase diagrams for binary systems. Okay, and so in the past few lectures, we discussed the phase diagram for a pure system, and so now what we want to do is extend the complexity to systems where you have two components. That's why these are called binary systems. Okay, so there's two chemical species, and we'll label them A and B for the moment. Okay. And in this case, we're going to look at liquid vapor equilibrium because it's relevant because a lot of chemistry is done in solution phase. So liquids in equilibrium with their vapors are important. So in this case, we have liquid and vapor in coexistence. And an important thing that we're going to assume in our discussion initially is that both phases, the liquid and the vapor, are ideal. Okay, and so this is an important stipulation that we're going to make in the following discussion until we transition into real systems. And the other thing that we're going to allow for is that both species A and B, they're both volatile, meaning that if they're in the liquid phase, they can escape. The molecules of either species can escape and then be present in the vapor phase. So in this case, this is again this idea of a dynamic equilibrium or an equilibrium where molecules are going back and forth. And already that should tell you something about the chemical potentials of the species A and B in the liquid and the vapor phases. They must be equivalent. Otherwise, we wouldn't be able to have a scenario where we would have liquid and vapor in coexistence. This coexistence would actually depend on the compositions. And what we're going to say is that for all compositions of both the liquid and the vapor, we have some combination of liquid and vapor present. Okay, and that's because the chemical potentials of both species are equal in both the liquid and vapor phase. Okay, so again, let me just remind you that remember for a single fluid, we had a pressure temperature phase diagram. And if we want something that looks like water, we see that the slope for the solid liquid coexistence line is negative, and we showed how that comes about from our analysis of dPdt last class at coexistence. Okay, so that should be no surprise. And it's related to the enthalpies, molar enthalpies of vaporization and the volume changes of molar volume changes of vaporization, or sorry, melting. Okay, so what we want to do is create a diagram for a binary system where you have two species and we are interested in liquid vapor equilibrium. Okay, so we're going to be interested in the equilibrium between a liquid and a vapor. And we saw from our analysis of the degrees of freedom for a system like this, which is 2, let's see, plus c minus pi, this Gibbs phase rule gives us 2 degrees of freedom for a binary system. Okay, we have this being 2 and this being 2. So 2 plus 2 minus 2 is 2. We have 2 degrees of freedom. And we're going to use those 2 degrees of freedom to specify temperature and pressure. Okay, in some sense. So we're at least going to use one of our degrees of freedom to specify temperature, let's say. And so in that case, what we're going to end up with is a diagram that will be a function of pressure and composition. Okay, so the degrees of freedom that we have, remember, are pressure, temperature, and since we have mole fractions, we can choose either YA or XA. Okay. And what those mole fractions are is a little bit more clear in this diagram that I've shown here. Okay, where we have our liquid in equilibrium with our vapor. Okay, and we can say that there's some temperature that we specify, okay, for the moment, and there will be some compositions denoted as Y, YA, and YB in the vapor, and denoted as XA and XB in the liquid. And we have our usual constraints that XA and XB have to equal 1, and same for the Y's, so the mole fractions. Okay, so that's the scenario here. This is really the system that we're going to address. Okay? I just want you to recall, not that we're going to use it today, but just recall for later, okay? Since both phases are ideal, the vapor phase is ideal, so we can treat it as ideal gas. So we have two ideal gases in the vapor. And we saw that the chemical potential for a species in a mixture of ideal gases is given by this expression. And so for species A, the chemical potential at a particular pressure, temperature, and YA and YB, remember Y's are for the vapor phase composition, that's going to equal mu A, the chemical potential of A at some reference state, plus RT natural log of the ratio of the partial pressure of A divided by the pressure in that reference state for A. And since it's a vapor and it's ideal, the partial pressure of A is just the mole fraction of A times the total pressure. And so we can then rewrite that expression in this form, okay, where now we've split up the YA times P. Okay, so that middle term is the P, and then the last term is the YA. And since there's a product, we can separate the logs into sums. And then we combine the first two terms in this expression right here into a reference state chemical potential, okay, which is some reference state. In this case, it turns out to be pure A at the temperature and pressure of interest, plus RT natural log Y sub A, which is the composition of the vapor. Okay, so keep this in mind, that if you have an ideal vapor, if you have a mixture which is ideal, and each one of those species is represented as an ideal gas, the chemical potential of each one of those species is represented as the sum of some reference state chemical potential, which can be pure, or it can actually be a combination. It can be a mixture, or it can be any phase you want. You get to choose what that reference state is. Okay, so that's what that first term is in the last equation on this page, plus RT natural log of the vapor composition of that species. Okay. So this is very important because this is the form that we're going to use to generalize to non-ideal systems, okay? And so this is something that you really need to understand, otherwise you won't have an appreciation for how we move on to non-ideal systems. So I introduced this here so that you don't forget to go back and understand this if you haven't already. Okay, so let's go on now. We're interested in a phase diagram. And that phase diagram is going to be of the form. Okay. So we're going to let pressure vary. We're going to say that temperature is constant. So we're going to specify temperature. T is something that we specify. Okay, so we're going to use one of our 2 degrees of freedom to specify temperature. So that means that we can then say, well, okay, either we let the composition, we can choose a composition and then find pressure, or we can specify a pressure and ask what the compositions are. And now we have 2 phases. We have a liquid and a vapor phase. So we're going to have to treat them independently. We're going to start independently in constructing this phase diagram, and then we're going to put them together. Okay, so the first thing we're going to treat is the vapor phase, which is a little bit easier to deal with. Okay. So on our phase diagram for this 2-component, 2-phase system, right, we're going to have pressure, and this is the total pressure, okay, in red. Now on the x-axis, we'll have composition. Okay, so we'll start with the gas phase first. So we're going to say that we have Y sub A. Okay, it doesn't make any sense to have Y sub B because once you specify Y sub A, Y sub B is specified for the system. Okay, so we really don't have to worry about Y sub B. I could have used Y sub B for the x-axis, but it really is irrelevant which one you use. At this point, we have Y sub A is equal to 0. Okay, so we have no A, it's all B. So this is no A, all B. Okay. And then here we have Y sub A is equal to 1, which means we have all A and no B. Okay. So we want to know then how the total pressure of the system, okay, in our system being this little box here with liquid and vapor, okay, what's the total pressure in the system? Okay, we know that we have ideal gases, right? So the question here is, how does P total vary with Y sub A? Okay, and so this is for the gas phase, this is for the vapor phase. In the vapor phase. Any questions on the on this? Is this clear what we're after? So we have a system where we have liquid in equilibrium with the vapor. Okay, we've specified the temperature. Okay, and so now there's going to be a total pressure that evolves or emerges because of we are specifying the temperature, and then there being different compositions, okay, in the vapor and the liquid. So the first thing we're going to ask is, well, what is the total pressure that arises once we specify the temperature and we say that we're at a particular composition? So we can then string all of the compositions to get a curve of how the total pressure varies with composition, right? You can say, well, all right, I've specified temperature. I'm going to specify a particular composition. So on this plot here, T is specified. I could pick a point. Here, I could say, well, if YA is here, what is the total pressure in the system? Okay. And then I can do this for a whole bunch of Y sub A values, and then I can get a curve. Okay, so that's what we're after here. So is that clear? Oops. Okay, so let's continue. So Y sub A. So P total, since we have ideal gases, is just equal to the partial pressure of A plus the partial pressure of B, because we have ideal vapor. Okay, and that's why it's important to have these stipulations. They allow us to move forward. And we know that the partial pressure of A for an ideal gas is just going to equal the composition times P total. And for B, it's going to be YB times P total. Okay, that's fairly straightforward. Okay. Is that makes perfect sense, right? Okay. Okay, good, thanks. So it turns out that for the liquid, okay, so if we're looking at an ideal liquid, okay, in equilibrium with ideal vapor, the partial pressures are given by a very simple formula. So the partial pressure of A is going to equal now the mole fraction of A in the liquid. So this is where we have a little bit of a need for care. Okay. So for an ideal liquid, okay, so remember we have in our system this liquid phase, which is ideal. Okay, it's going to exert a partial pressure. The liquid, remember we said that molecules can escape from the liquid, and as molecules escape from that liquid en masse, right, there's not just one, but there's many, statistical amount, all of those particles moving into the vapor are going to exert a pressure. That's the partial pressure now coming from each one of the species in A, okay? So essentially it's a momentum that's being transferred. So A is going to have some pressure being exerted above the liquid, and B is also. So the contribution of A from that pressure of molecules escaping from the liquid is written as X sub A times PA. We call this saturation or the vapor pressure of A. So if A were alone at these conditions, right, if we had pure A, at temperature T, it would exert a pressure, it would have a vapor pressure, right? And so what that means is that if you go back to our phase diagram represented for a single fluid, so if we pick a temperature and we had pure A as a liquid in equilibrium with its vapor, what would be the pressure that we would see? Okay, so in this case, if we picked our temperature to be here for pure A, and we had liquid vapor coexistence, we would move up to the liquid vapor coexistence line and we would read off this pressure. So that's the pressure that pure A would be exerting above that liquid if it were in existence at that temperature T. Okay, if we had coexistence at that temperature T. And so then this guy becomes the vapor pressure of A at that temperature that we're interested in. Or we can say that's the vapor pressure. Okay, that's another thing. And I think your book uses P star for the vapor pressure. I like to use saturation pressure just because that for other reasons, but I won't get into them. So that's what we have here. So this is called Raoult's law. And again, it's one of these things, it's not really a law, it's just a model. It's just telling you how to relate the partial pressure of a species in the vapor, okay, if you have liquid vapor equilibrium, to the mole fraction of that species in the liquid phase. Okay, so this is very important. So write it down. Okay, that what this is saying is that if I have liquid vapor equilibrium, okay, and if I have A and B in the liquid and A and B in the vapor, the partial pressure of A in the vapor is related to the mole fraction of A in the liquid. Okay, that's very important to keep in mind. This is not Y sub A, it's X sub A. And remember, we said by convention, the X's represent liquid mole fractions and Y's is vapor. So this is relating the partial pressure of A in the vapor to its composition in the liquid, X sub A, times the vapor pressure that you would see at a particular temperature T. Okay, and we can actually put in T here because we're interested in the system at a specified T. Remember, we specified the temperature T. Okay. All right, well, this is interesting. Let me think about this. In this case, what this is saying, Raoult's law, okay, and it's not a law, right? It bothers me to say that, but you can maybe see me squirm when I say Raoult's law. But anyway, what this is saying is that the partial pressure of A at a particular temperature T in an ideal, above an ideal liquid, in the ideal gas, the ideal vapor above this liquid, is the mole fraction times a constant. Since we specified temperature, since T is specified, okay, the vapor pressure of both species, A and B, is going to be specified. Okay, it's a constant at this temperature, okay, because we specified the temperature, all right? So this guy is a constant, all right? The only thing that varies is X sub A here, okay? And we know that the P total in the vapor is a combination of X sub A, P sub A and P sub B. Okay, let me just write down P sub B, which would just be P sub B is equal to X sub B times PB saturation at that temperature. Okay, so we have these two relations, the Raoult's law for each case. Okay, did I make this clear for everyone? Is there any confusion? So in this case, PA sat and PB sat, these vapor pressures are constant. So in fact, it seems that, all right, maybe we can actually ask, what is P total, which is the sum of PA and PB? How does it vary as a function of X sub A? Let's do that, because it seems like P total is a sum of PA and PB, but PA is really just mole fraction of A times a constant, and PB is just a mole fraction times a constant. So it seems that that's actually easier to do. And in fact, I can write X sub B as 1 minus X sub A times PB sat. So in fact, I could actually get P total all as a function of x sub A, right? So here's my expression for P total. Because it's an ideal gas, it's just a linear sum. So P total is equal to PA at this temperature plus PB at this temperature, but we know what PA and PB are. PA is just XA times PA saturation at this temperature, and PB is just 1 minus XA times the vapor pressure, saturation pressure of B. So you see here that P total actually is very simple representation in terms of X sub A, right? And some constants. And those constants come from the pure single fluid phase diagrams at this temperature. Okay, so all you have to do is if species A is methane and species B is, I don't know, octane or whatever, ethanol or something like that, you look at these tables and you find that data. And so those remain constant for the temperature of interest. Okay, so now we know then that the pressure total is just going to vary as a function x sub A. Okay, we could have used x sub B, but we know that they're related, so it's okay. We can use one or the other. So in fact, what we'll do now is to say, all right, well, before we go to y sub A, what we'll do is we'll actually change this and we'll use x sub A. All right, seems like x sub A might be a good way to do this. Okay, and so that's fine because we can still have x sub A here is equal to 0. And here, x sub A is equal to 1. Okay, everything still, in terms of what it means physically, is the same. We have no A on the left, and we have no, all A on the right. Okay, all right, so that seems to be a pretty good idea. And in fact, if we choose x sub A, right, before we discuss y sub A, all right, it seems that P total is linear in x sub A, right? And that's actually a good thing. It's linear and lines are always good. So what we see here from this expression, right, that P total is a function of x sub A. It's also a function of T. Okay, so let me be clear that it is a function of T, but we've specified T, but it becomes a function of x sub A, right? And we see that this is linear. And that's always good when something turns out to be linear. There is no xa squared, xa cubed, natural log xa, e to the xa, etc., etc. It turns out to be a linear function, and that's always good. So that means that for our two-phase system now, if we want to look at the total pressure in terms of composition, we get a line if we were to consider P total as a function of x sub A. Okay. We could have done x sub B again, but I just chose x sub A. So this just turns out to be a line, and that's a good thing. Okay, and that line is given by this expression. So let's actually now plot this line. Okay, and what we're going to do is we're actually going to seek recourse into the fact that each one of the individual components to P total, right, PA and PB, are also lines. So PA right here is a line. If we plot PA at this temperature, the partial pressure of A at this temperature, as a function of the mole fraction A in the liquid, it's a line, right? The slope is PA sat, and we know that it's a dependent variable is x sub A. Likewise, we see here for P sub B, it's also going to be a line, right? There's going to be an intercept, which is P sub B sat, okay? But then it's going to be dependent on x sub A as minus xa times PB sat. Okay, when you just do the multiplication through the 1 minus xa term. So both of these PBs and PAs, the PA and PB are lines. Okay, so let's start with that. So PA is given by this expression. Okay, so when xa is 0, PA is 0. And when xa is 1, PA sat, PA is going to be PA sat, right? That's pretty obvious. So if you go back to our line, when PA is 0, when xa is 0, the partial pressure that we see here from A is going to be 0. And when x sub A is equal to 1, it's going to be the vapor pressure of A, which is PA sat. Okay? And so we'll let that be here. So this is PA sat at T, and it's a straight line. Okay, remember, PA of T using Raoult's law is XA PA sat. So when XA is 0, PA is 0. When XA is 1, PA is equal to PA sat. And so we can just draw this line. And I'm going to try to make it a line, but it may have some curvature just because. Okay, so that's the line that represents PA. Okay. And now PB is equal to 1 minus XA times PB sat at T. Okay. That's just going to equal PB sat minus XA times PB sat. Okay. If I've done the multiplication. So when XA is 0, PB is going to equal PB saturation. Okay, and so we're going to let that be another color. Let's see, let that be, we'll put that in black. So that's right here. Okay, so this will be PB sat. Okay. Again, that's using this expression right here. When XA is 0, PB is equal to PB sat. And then when XA is equal to 1, we get 0, right? When XA is equal to 1, we have PB sat minus PB sat. So it's going to be here, 0, when XA is equal to 1. And so the partial pressure contribution from B will be this line. Okay. Any questions on what I just did there? Okay, and so it all hinges on this, right? Raoult's law. But we know that the total pressure is just the sum of the two. We know that the total pressure at any composition, as we go from XA equal to 0, XA equal to 1, is just going to be the sum of the two. In this case, because it's an ideal gas, an ideal vapor. And actually, that's very simple because all you have to do at any given point is just add the values that you read off from the two curves. Okay, and so we can see the endpoints are quite clear. For P total, when XA is 0 and when XA equals 1, there's only one contribution, and those contributions are shown here. When XA equals 0, this is the contribution, and when XA is equal to 1, this is the contribution right there. So it must be that those 2 points are connected by a line. Remember, we said P total is linear in X sub A. This is a nice straight line. There's no quadratic terms or any whatever terms in X sub A, depending on X sub A. So we have these 2 points. They must be connected by a straight line because the curve for P total as a function of X sub A, we already deduced is a line. And so it turns out very nicely that the line you get for the total pressure just connects PB sat and PA sat. And this is the total pressure. So this is the curve that gives us the total pressure in the system as a function of the mole fraction of A in the liquid. So this guy is P total right here. Right there. As you see, it's a nice straight line, and that's always good when things come out linear. Okay, and it's linear because we've assumed that the liquid and the vapor are ideal. Okay, so as we are moving along and constructing the phase diagram for this binary system with liquid, vapor, and coexistence, what we've so far determined is that the total pressure in the system, once we specify temperature, okay, once we specify temperature, that's one of our degrees of freedom. We're left with one more degree of freedom. But once we specify temperature, the total pressure in our system is going to vary as a function of X sub A. Okay, that's the simplest way we can represent the total pressure because it turns out to be a line. Okay, again, it's because we've assumed ideality of both phases. And that total pressure curve is this. Okay, so along this line, okay, I'm going to ask a question now. Along this line, okay, not at x sub a is equal to 0 or x sub b or x sub a is equal to 1, but anywhere along this line, okay, all right, how many phases do we have? How many phases do we have along that line? In fact, we can say all along the line. How many phases are there? So that line represents how many phases?
2.
Yeah, who said that? Sorry.
Sheldon.
Sheldon, okay. Yes, you're exactly right. There's 2 phases. That's exactly right. Okay. So that curve is representing a system where we have 2 phases in equilibrium. Okay. Those 2 phases are a liquid phase and a vapor phase. Okay. And the x-axis represents the composition of the liquid phase. So anywhere along that line, we have 2 phases in equilibrium. The x-axis is telling us what the composition in the liquid phase is. And then when we read up to that curve, that magenta or purple, whatever color that is, we see that we get the total pressure for the system that has 2 phases and 2 species in each one of those phases. Okay. When we go to the endpoints, we still have 2 phases, but now we only have 1 species, either B or A, depending on which side you're on. Okay, but we still have 2 phases. And we still have 2 phases is because the pressure that we are plotting here is the vapor pressure of the pure species. On the left, it's pure B, and on the right, it's pure A, right? We have this PV-SAT, or the vapor pressure of each species at the endpoints. And we know that the vapor pressure, that vapor pressure at this particular temperature, we determined from this point, remember? And this point is a point on the coexistence curve for the pure species. So we have 2 phases all along that curve for the P total. Okay. Even at the endpoints, we have 2 phases. But in that case, we only have pure component A or B. Is that clear? That has to be penultimately clear to everyone. It has to be clear.
It's clear.
Okay. Thanks for the feedback, Sheldon. At least to one person, it's clear. All right. All right, let me just, okay. So we haven't said anything about the vapor phase yet, okay? So this is just a liquid. I start liquid compositions here. There was something, what did I want to say, but I forgot. Oh, it'll come to me. All right, so this is a very important line, okay? So that represents 2 phases. So let me rewrite that just to be clear. So now I'm just going to recapitulate that line. Okay. So here x of A is equal to 0. X of A is equal to 1. Okay, this is P total. Okay. T is specified. Oh, right. Now I understand what I wanted to say here. So we specified T, that was one of our degrees of freedom. We're left with 1 degree of freedom. Okay. So based on this, we see that if we specify a pressure, a total pressure that we want our system to be existing in, right? Our composition is set for us. So T is specified. Okay. If I say, well, I want this pressure, let's say I pick this pressure. Okay, and I want 2-phase, 2-component equilibrium, binary liquid vapor equilibrium at this temperature, then my composition and pressure, then my composition is specified for me. I have no choice but to accept this as my composition, okay, in the liquid. And of course, we'll see that that also is going to hold for the vapor. My vapor composition cannot be something that I determine. If I wanted to specify a composition of the liquid, okay, let's say I wanted to specify this is my composition of the liquid, let's say X sub A prime, then the pressure that I would need to operate under to have two-phase, two-component equilibrium is, I just read up, it would be here. I have no choice what that total pressure would be in the system. And of course, I can't control the partial pressures. I mean, right, the thing you're controlling in the system is the total pressure. Okay, we can't really have a partial pressure stat. So what you're controlling is the total pressure of the system. So is that distinction clear now? This is the application of Gibbs phase rule. Okay, so we see here that once we specify T and we choose either one of the other pressure or composition, the last variable is specified for us. Okay, and now another important conceptual idea from this. Here I've reiterated our phase diagram, at least the boundary of the phase diagram. So that was a boundary. So we know that along that line, we have, as Sheldon pointed out, we have two phases in coexistence along this line, okay? So along this line, there's two phases in coexistence, okay? So this is X sub A, all right? This is PA sat at T, and this is PB sat, vapor pressure B at that temperature, okay? And the line represents total pressure, total pressure as a function of mole composition in the liquid. Now, so we have two phases here, okay? What happens here, okay, if I raise the pressure? So let's say I'm at this point. Let this be this triangle point right here. Okay, so we know I'm at a composition X sub A and X sub B, and I'm on this line. So I have two phases in equilibrium. The total pressure is given by the value, whatever that is on that line. Okay. Now what happens if I increase the pressure? So I have my system, it's at equilibrium initially at this point. Okay, it's two phases in equilibrium with composition X sub A in the liquid. What happens now if I increase the pressure at this temperature? So I'm going to keep the temperature constant, but I'm going to increase the pressure. Anyone want to take a guess? Even if I were here, let's say if I were here, right? I know I'm on the line, so I must have two phases. But now as I increase the pressure, right? So let me ask you this. What happens at the end? What do we have at the end? Do we have a two-component system, or do we have a one-component system at the endpoints of this line?
One component.
One component, exactly, Khalil. Now, if I'm at those endpoints where I only have one component, again, we said anything along the line has two phases. Okay, so this whole line represents two phases. So at the end, I'm going to have either pure A or pure B, and I'm still going to have a liquid vapor system, but it's just going to be of pure A or pure B. So if I'm at one of these endpoints and I increase the pressure, so let's say I'm here, okay, I know I'm on the line, so I have liquid and vapor in coexistence. I'm going to increase the pressure. What's going to happen in that pure system is I increase the pressure.
Does it become mixed or more mixed?
What do you mean by mixed?
The mole fraction of the species, departs from just one.
Well, it's pure, so X sub A is going to be zero. Well, X sub B is going to be 1. there is no other option, right? We're not moving along X, we're going up. All I did was increase the pressure. It's pure, so the mole compositions will never change. So I'm starting with a two-phase system.
You only will have one phase.
Ah, okay, very good. It will only have one phase. Okay, that's right. Can you tell me which one?
A liquid.
Ah, very good. Can you tell me why? You're right. And why is that?
Because if you decrease the pressure, you'd have more gas or only gas. But because you increase it, you'll have liquid because you're putting more pressure on everything. So it's staying in the liquid phase.
Exactly. Very good. Very well done. That's exactly right. So at that point, if I increase the pressure, keeping temperature constant, I'm going to liquefy everything. Everything becomes a liquid because as you increase the pressure, okay, you can think of it in a couple of ways. If you have vapor above the liquid and you now decrease, if you increase the pressure, well, you're going to get less and less vapor until you get all liquid. The other way to think about it, and since we have pure fluid at that endpoint, if you're starting at this, so this is a pure fluid phase diagram. If you're starting here where you have liquid and vapor, remember, okay, at a particular temperature T, which doesn't change, as you increase the pressure, it becomes all liquid. Okay, and so what that says is that if I start at this point and I increase the pressure, I'm going into an all liquid regime. And the same thing here, because it's the same argument, I increase the pressure, I'm going to have liquid. At any point along that line, then, if I increase the pressure above that line, I'm going to have liquid. Okay. I'll still have liquid with both A and B now, because along the line, the mole composition is no longer in favor of one or the other. Now I have a mixture. Okay. But what does change along the line, if I increase the pressure, is that I get liquid. So this region above the line represents all liquid, but we have X of A and X of B as our composition. That line represents both liquid and vapor in equilibrium. Okay. Anything above that line represents all liquid. So what we've done now is actually get a boundary. We've said, all right, if composition is the thing that we're sort of looking at here, okay, as this intensive variable, right? X of A is intensive, it's independent of amount you have. We've actually mapped out a phase, at least one phase, which is the all liquid phase. Okay, so at a particular temperature, keep in mind, all right, we've mapped out a bunch of values of total pressure and composition where we have all liquid. Okay, and what we've also done is mapped out the boundary where that all liquid system now begins to have vapor in it. Okay, and so along that line here, okay, we've reached the edge. Okay, so let me put it to you this way. If I start here, right, which is all liquid, of course it's still binary because the liquid can have a composition. There's no reason why a liquid can't be a mixture. So it can have X of A and X of B. But now if I start decreasing the pressure, right, I'm going to have all liquid, all liquid, all liquid until I hit this boundary right here. And at that point, I'm going to start making vapor. Same thing if I were to start here, I have another composition, but it's all liquid. I'm going to start decreasing the pressure until I hit this point right here. And I'm going to start making vapor. Because we know anything along that line, we have liquid vapor coexistence. So what we've done right now is to map out all this region where we have all liquid and then the boundary, okay, in terms of pressure and composition, where that all liquid system now starts beginning to have vapor. And now we're going to have some coexistence. Okay, so that's what we've done so far. And this is all in terms of the liquid composition. I haven't said anything about the vapor composition yet. Okay, is that clear?
It's clear.
Okay, so far it's, what you see on the graph is what it is. We don't bring in anything else. We haven't said anything about the vapor composition or anything like that. So all we've done so far is map out the liquid part of this binary system, this two-phase system. All we've done so far is map out the liquid part, okay? And of course, when you consider the liquid part of this system, you have to come to the edge where that liquid now starts becoming or having some vapor in existence, in coexistence with it. Okay, so that's what that means. We've mapped out this region of liquid and its boundary or its horizon between where it starts making vapor. And so that's what that line is. Okay, and it's of course in terms of the variables pressure and composition, total pressure and composition of the liquid. So the next thing now we have to ask is, well, what's going to happen here as a function of the vapor phase composition? Okay, we need to sort of figure out how to deal with that. So along this line, all we have information about is the liquid phase composition as it is related to total pressure. Okay, but we know nothing about the vapor phase compositions. We don't know how they behave. And I tell you that it's not linear. The vapor phase compositions as a function of total pressure is not linear. So that's what we have to address now. So the next question, and I'll just leave you with this. Next question will be, which is for Friday. How does P total vary with Y sub A? So that's the next question. So today we found this. Okay. Next class, we're going to ask and solve and answer how does P total vary with Y sub A? And we're going to then plot both of those results on the same plot. So what we're going to have at the end of next lecture is we'll have P total. We'll have X sub A and Y sub A. Okay, so X sub A equals 0, Y sub A is equal to 0, X sub A is equal to 1, Y sub A is equal to 1 at these 2 points. We already found this out, okay, today, and this is all liquid. Okay, with the varying composition of X sub A and X sub B along that line. Okay, next class, we're going to figure out the vapor part. What does that line look like? Okay, what is P total as a function of Y sub A at this temperature? Okay, that's what we'll find out next class. All right, I'm going to end there. There was a lot in this lecture, so I hope everyone will go back and really digest it. Okay, it's very interesting stuff, and in fact, very relevant to solution chemistry and separations. Okay, any questions or comments before we leave? Okay, well, enjoy the Wednesday. If you're in Newark, it's a great day so far. Winter is slowly encroaching upon us, but try to get some sun and enjoy the outdoors if you can. Be well, and I hope you are all safe and well. Okay, take care.
Thank you.
Thank you.